Hey, welcome to the fifth part of the section on Taylor series. Just a quick recap of what we learned so far. For a function y that can be differentiated n plus 1 times on the interval from the point A to the point x, we have that y of x minus something that we called on of x is equal to the sum from k equals 0 to n of y differentiated k times at the point A divided by k factorial times x minus a to the power of k. And we also learned that if these on of x's get closer and closer to some number as n tends to infinity, then we can take the limit as n tends to infinity of both sides. Well, the limit as n tends to infinity of this side, we only need to worry about this part because that y of x doesn't even depend on n at all. So the limit as n tends to infinity of this side is actually y of x minus the limit as n tends to infinity of on of x. And that's equal to the limit as n tends to infinity of this thing. Well, to rewrite that, we now have y of x minus, and last time we called the limit as n tends to infinity of on of x, we called that L. Let's continue to do so. So y of x minus L is equal to the sum from k equals 0. Well, we're taking the limit as n gets to infinity. In other words, as we keep adding on more and more terms, what number does this side get closer and closer towards? Well, as we keep adding more and more terms on, it gets closer and closer to some number, and that number is what this infinite sum is supposed to represent. It doesn't mean we keep adding things on forever. It's impossible to keep adding things on forever. We'll die long before we get to infinity. So yeah, it's just what do these sums get closer and closer towards the more terms we add on? That is what this infinite sum means. Okay, so it's the sum from k equals 0 to infinity of this thing, of y differentiated k times at the point A divided by k factorial times x minus a to the power of k. And this thing on the left-hand side is called the Taylor series of y of x. If a equals 0, it's called the Maclaurin series. M-A-C-L-A-U-R-I-N, I think. Maclaurin series. Yeah, that's right. So this thing is called the Maclaurin series of y of x if a equals 0. That's a special case. Don't worry too much about that. I personally just call it all the Taylor series. But hey, if you want to remember Maclaurin series as well, you're very welcome to do that. So we also learned, and this is kind of a subtle point, we learned that the Taylor series is not necessarily equal to the function y of x. In fact, they're only equal if this limit as n tends to infinity of on of x equals 0. And we're going to learn in this section sometimes we can tell that that's the case. In some ways we can show that to be the case. So that's what this little part's all about. Okay, so to do that, let me start off with a drawing. It's going somewhere, so bear with me. This is x-axis, y-axis, and we got a function. So this is our yeah, all right, fine. This is our function, and this time I'm going to call it f of x just to be different. Okay, so here is the point x equals a. Here is the point x equals x. Sorry about the notation there. And this point here, I'll still use black. This point here is the point x equals c, and f of c is equal to some number called k. K equals f of c. And c is the point such that we get the biggest value out of the function f along the interval from a to x. So that's what c is. Okay, now we're going to do a little bit of integration here. We know from the fundamental theorem of calculus that this blue area under the curve is actually equal to the integral from a to x of f prime, and now we need a dummy variable, f prime of t. We need a dummy variable because we already used the x here. So f prime of t dt. That's what that blue rectangle is equal to. Sorry, blue area under the curve is equal to. Now we're going to do a rectangle though. So we're going to make a red rectangle, and the red rectangle is going to be this one here. And this red rectangle, we can see it has area of the width times the height. Now the height is the maximum of the function on that interval, which is f of c, which is equal to k. So the height is k, and the width is going to be, well, this distance here, which is x minus a. Okay, and now for the interesting part. This is equal to k times the integral from a to x, just of the function 1 dt. It's equal to k times that integral. And well, the reason for that is if you integrate, there's an invisible 1 here. If you integrate the function 1 dt, you're just going to get t. Then you put x into t and a into t, so you get x minus a when you do the definite integral thing. Okay, so what we learned here is that this red rectangle has bigger area than the blue integral, and so we can say that this blue integral is actually less than or equal to k times the integral from a to x dt, where k is the biggest value of f along that interval. So that's very important. Okay, now we're going to do something with the ON of x's. Okay, so we know that ON of x is equal to the, what is it equal to again? Yeah, the integral from a to x of the integral from a to t1. Keep going all the way up to the integral from a to tn of y differentiated n plus 1 times at the point, with the dummy variable tn plus 1, dtn plus 1, all the way down to dt2 dt1. Okay, now I want to suppose that y prime, y prime prime, all the way down to y differentiated n plus 1 times, along the interval from a to x, all of these functions are less than or equal to the number k. So this number k is such that along the interval from a to x, we have all the function and all of its derivatives are less than or equal to that number k for all values on that interval. Okay, so what now? Well, we can do the same trick that we just did with the function graph and pull k all the way out. We can pull k all the way out. So we can say that ON of x is actually less than or equal to k times the integral from a to x, the integral from a to t1, all the way to the integral from a to tn. And now we've yanked the k out because k is bigger than all of these functions. Okay, and now it's just dtn plus 1 all the way down to dt2 dt1. And now the real magic, we showed earlier on that in fact when you just evaluate all of these integrals like that, all you get is going to be k, or all you get is going to be x minus a to the power of, how many integrals are we doing? 1, 2, well, n plus 1 of them, because we start out at dt n plus 1 and end out at dt1. So it's going to be x minus a to the power of n plus 1 divided by n plus 1 factorial. So ON of x is less than or equal to k times x minus a to the n plus 1 divided by n plus 1 factorial. Let me write that on a new page. So we have on of x less than or equal to k times x minus a to the power of n plus 1 divided by n plus 1 factorial. Now, let's suppose that actually along the interval, so along the interval a to x, along the interval a to x, all derivatives, D-E-R-I-V-A, derivatives, all derivatives are less than or equal to k. And let's suppose that the function can be differentiated infinitely many times. So in other words, yn is less than or equal to k on that interval for all n. Well, what happens as n gets bigger and bigger? Limit as n tends to infinity. Let's take the absolute values. Limit as n tends to infinity of this thing. Well, this is going to be the absolute value. This is going to be the absolute value of k times the absolute value of x minus a to the power of n plus 1 divided by n plus 1 factorial. Well, as n gets bigger and bigger, this n plus 1 factorial is going to get huge. It's going to get really, really big. It's going to get really, really big compared to the x minus a to the power of n plus 1 term on top. So the bottom term is going to get really, really huge compared to the term on top. Think about how big factorials get, because there's no, you're timesing x minus a by itself n plus 1 times, but x minus a is a fixed number, whereas n plus 1 factorial, there's kind of no bound to how big the numbers you're timesing by each other get. You could be timesing by 100 billion gazillion when n is that big. So yeah, the bottom part gets really, really big to the top part. Compared to the top part, the bigger n gets, and so this whole thing gets closer and closer to 0. And so, in fact, this limit is equal to 0 when we have that y of n is less than or equal to k on the interval a x. So whenever we put anything between a and x into the nth derivative of y function, we get something that's less than or equal to the number k, then it means that this limit of on of x is going to be equal to 0, and hence we therefore have that our function y of x is equal to its Taylor series. So y of x is equal to the sum from k equals 0 to infinity. Again, we're not adding it together infinitely many times, but we just say to infinity because the terms get closer and closer towards some number the more we add on. So it's equal to the sum from k equals 0 to infinity of y differentiated k times at the point a divided by k factorial times x minus a to the power of k. All right. Thanks very much for watching. We're going to do an example of that in the next part. Don't forget to download the notes and have a look at the exercises. See you guys next time. Thanks for watching. Take care. Bye.